So this is a getting started tutorial for Autodesk Robot Structural Analysis. And it's really aimed at those planning to use it in the design studio or who might want to consider it. So I've already covered the Oasis GSA software package, so that's the series of ad hoc videos that you can see uploaded to the channel. And in those, I covered the GSA package from getting started through to how to use it to get the data that we require out of the analysis to carry out the design process. And really a lot of what's covered there can equally be applied to robot as well. So a lot of that material is valid and you might still want to look at that even if you do choose to use robot. Vice versa, a lot of the information we're going to cover in this video can equally be applied to robot, to GSA, or also other software packages. Because as I said in the lectures, if you understand the analysis and modelling process, you should really be able to apply that to almost any software package. So this is the model I'm going to be looking at in this video. So as you see, it's now fully constructed. It's meshed. If I turn on the mesh, you should be able to see that. There we go. So it's obviously quite a well-developed model. So if you're new to robot structural analysis, you might be wondering, well, how do I get to this point? So what we have on the Autodesk website is a really good set of tutorials. So it's in their quick start guide, and I'll put a link to this in the video description. But you can see on the screen now there's a whole set of short videos that essentially cover the essentials of using the software. And as you might imagine, it starts with the user interface and then goes through various different types of modelling step by step. So I'm not going to cover all of this here. There's not much point because we already have this really good set of tutorials. So they're all very short videos. They're all quite concise. And I think if you spend a bit of time on this, you'll very quickly learn how to use the fundamental features, the basic features of Autodesk Robot. So certainly starting with the module on the user interface, you might then want to perhaps skip ahead to modelling concrete structures perhaps, because after all this is the concrete structures design studio, how to apply loads, the analysis process, if you really wanted to, a bit on actually using the design modules that are built into the robot software as well. And if you really have time and maybe are familiar with Revit and BIM, again, the final video here might be of interest to you if you're working in Revit and to get the connectivity between the Revit software and robot. Again, they're both by Autodesk, so again, it's the kind of ideal combination. But what then I'm going to do for the rest of this video is I'm going to cover a range of specific points that are aimed at really helping you to model the structures that you're designing, to then get the information out that you require to help you really get started in extracting the data if you choose to use this particular software package. So I'm now back with my robot model. But before looking at the analysis side of things and the results that we can extract, I want to maybe look a bit at the CAD background I'm using and how we can use the CAD side to our advantage in terms of importing that into our Autodesk robot model. But just before getting into that, more of an aside, so you can see here the robot screen. This might not look quite like yours because I've added in, or I'm permanently displaying the toolbars that I use often. But the thing I wanted to point out is this small bit of the user interface down in the bottom left corner. So I have no idea why they made it this small, but I just wanted to remind you that these tools are here. The one that I think is key and that I think you definitely should use or have a look at is the one there, which is the 4 squares. Now I use that so often. If you look up here on my toolbar, I've actually made a custom toolbar. Essentially I've customized it because it's the dialog option to call up the display settings. So you can sort of find a set of display settings that you maybe are always using. You can select those, and then using the options at the top of this, you can then choose to save that. So each time you start the software package, it'll remember it. So it saves you reapplying the annotations each time. And maybe just before moving on, to maybe have a quick look at the actual model just before I go into the CAD side. The thing that we're seeing here obviously is the slab. We can see stick columns. But one thing that I think is really good is instead of showing the columns as being solid, so again we've got another set of very small buttons down here in the lower left that toggle node numbers, bar numbers, etc., etc. Again, if you mouse over these, you get tooltips. But rather than showing the full section, in a bigger model, this can become a bit, well, I think it can make things harder to see. I usually have that turned off, but because I still want to know what the section shape is, as much really as a cross-check to be sure I've put in the sections correctly, you can see the annotation there. So I've got my columns, they're square, and this kind of oversized square that you sort of see here is indicating the section shape. So I think that's quite handy. And if you go into the display, so again, choosing those four squares that you see there, going into bars, and then if you click symbol, that will either turn on or off the section shape. So again, I think that's a really handy feature. And again, personally, I think it's good because it's, again, a very graphical means of sort of checking our analysis model. The only other thing I'll mention just now is if we come down to the lower right, again, there's a few, again, very small buttons here which can take off the annotations completely. But there's this option there which you can see is faint until you mouse over it. And what that is essentially it's a graphical section plane. So the blue, the green and the red essentially are the same, correspond to the axis. But if I say go to my x-axis, I then sort of pull it in, you can see it's changing the cut plane. I can alter the transparency bit, which basically controls the bit which has been removed. So again, it allows me to still see a bit of it. So again, this can be helpful if you just want to maybe see a bit of your model. Again, zooming in and out, you can turn it around. So although it's not it's especially useful in the view that we've got on the screen now, you can imagine if you've got a results view, again, it can be really handy to be able to just cut back part of the structure just to make it easier to visualize things. So I said I'm going to go on or talk about the sort of CAD backgrounds. So the CAD background is this sort of faint blue lines that you see here. So if I mouse over it, so it's now selected it basically, so you can see that's the imported file that I've got for my background. As with most software packages, now I think you've got the legend type to display these tree menu. And here, if I go into backgrounds, that's my background file. If I right click on the screen, if I choose object properties, that then essentially reminds me of the options that I've chosen when I've imported it. So I'll look at the CAD file in a second, but here if we change to layers, you can see these are all the layers in the CAD file. So if I wanted to, I can maybe toggle them on or off. If I say toggle off the grid lines, I choose apply, and you see now that's taken off the blue lines which I used to mark the grid lines. I'll turn it back on. So again, it can be really helpful in terms of constructing the model itself. But just to show you what the starting point was. So if I start a new project, so it's going to be completely blank. I don't want to save this. close that. Personally, when starting a new project, I'd always go for the building design one. One of the reasons for that is by default, it gives you two views, a plan view and an isometric view. So again, it's just a nice way to work with the software itself. But in terms of the CAD file, so this essentially is my CAD model. It's just a basic 2D CAD model. You can see in my layer properties, I've got my U1, which I'll come on to, which is the first shear perimeter. And there's a reason for that. I've got layers for my slab, for my grid lines, for the columns. So again, here the yellow line is the edge of the slab. The red line is my grid line. So within Robot, I can actually define these and use them to construct my model. You can see I've got my columns. In this instance, I put them in as squares and rectangles, just because that's, well, in practice, likely to be what you actually have. The dotted green line that you see there is what I'm saying is my punching shear perimeter, or a punching shear perimeter. And again, I'll come back to why we might want to show this a bit later in this tutorial. So that's my CAD model, all very simple, all very straightforward. So if I now go back to Robot, in the File menu, I can come down to import the background. I choose the background file. But before continuing, one of the kind of key settings I think to be sure is ticked is the option to link it. So what that means is that even after you've imported it, if you make changes to the CAD file, they'll then be uploaded and synced essentially to the background that you've got in your robot model. And I'll show you why you might want to do that in a few seconds. So if I choose OK, there's then an option in terms of the coordinates it's inserted at, and my CAD model is in millimeters, so I will change that. If I choose apply, you'll see the units change. So these are meters. So obviously my slab isn't 25,000 meters long. So that's now looking more reasonable. It's in the AutoCAD tutorials that I pointed you to, but in the options here, if you choose the wrench option, you can look at the job preferences and the actual the preferences in the software itself, and then set your units. I can go into layers, and again, these were the layers that we saw in the CAD model. Again, it's up to me. I can choose to import them all or only a selection. But again, I can import them all now, and then as I showed you, you can turn on and off these, again, to suit your particular needs. So let's go ahead, select that, we choose OK. But here I've got my CAD background. Again, if I select Object Properties, it brings back up the dialog. So that's really it. I've got my CAD background, and I can now use that to construct the model itself. So let's return to the robot model that I started with. So here you can see the complete model on the screen. And just to make the point about how useful the link feature can be between the robot model and the CAD model or the CAD drawing. So if I go to the plan view, now for example, let's say I had maybe a penetration I'd missed out, or perhaps I want to put it in another column, or perhaps a wall. So yes, I could work out the coordinates for that and put those in by hand, but there's an easier way. So if I go back to the CAD model, and let's, for example, say a wall in one of these bays that either I forgot to add in, or maybe it's part of the design development. So I'll just switch the layer to columns. And then simply, maybe my wall is going to be something like that. If I then save this, what's going to happen is when I return to the robot model, I get this dialog coming up telling me that the CAD background's changed and asking me if I want to actually update it. So you can see just now there's nothing shown there in terms of the CAD background. If I click yes though, we can see it's imported or updated the CAD background to include the line of the wall. So all I then simply do, for a wall, again it's the same if you were putting in additional bits of slab, maybe a penetration, maybe columns. There's the various tools that you see here on the top right. If I choose the wall option, I've already got walls or wall types defined. So let's pick a 250 thick wall. Depending on how you define the model, it will give you the option to draw the wall in and either put it above or below the slab itself. So here I'm putting in a wall. It's going to be below or being drawn from the plane of the slab downwards, so down Z, and the height of the wall is going to be 3.6 meters. So quite simply, all I do, it's already, well, I've got the beginning and end points there. So if I simply go to the end of the wall and you see the cursor changes, or you get a square around the end of the cursor to show it snapped to that line on the CAD background. And again, it's maybe worth zooming in just to make sure it does snap to the point you intend. So that's gone to that point. Then finally to the end point. And if I just click close, that's then added in the wall there. So this can't really be seen just with the view settings that I've got on the plan. But if I go back to the three-dimensional view, to the isometric view, you can see here that's the wall I've added in. So again, that's adding in a wall. You can do exactly the same thing with additional columns, maybe add in beams, put in penetrations, and maybe you want to put in lines to apply load to. Again, the CAD backgrounds give you a very easy way to give you a reference to constructing your analysis model. So we're now back with our completed model. So we've completed the model, we've meshed it, we've analysed it, and we're now ready to look at the results. So I've applied a uniform load to this. I've applied a factor just to give us some reasonable forces. So now I'm going to look at the results. What I'm going to show you in this part of the talk is how we can best use the contouring to help us with our design. So in Robot, if you look at the top center, we can change the dialog there to results. There are various types of results we can display, from diagrams to maps to a detailed analysis. But we're going to look at the results maps in this case. So that then switches to a results view. I've got my load case there. And then you see on the right, these essentially are the options that we have associated with the results. So you can toggle along the top with the arrows there, or there's a collapsible menu at the side that allows you to quickly jump between the options. So let's, for the sake of argument, look at the bending in the XX direction. At the bottom, there are various options which I'll come back to, but I'm just going to look at the map of the contouring to start with. So if I hit apply, you see nothing's actually happened. And that's because I think it's maybe defaulted to a very high contouring range, perhaps associated with work I've been doing previously. So if I go to scale, either from the menu at the side or by toggling along the top, if I change it to linear scale, I normalize that, and then we can then see it's essentially rescaled the diagram to the values that are in the analysis. So just to make it easier to look at, if I go to the top view. So remember, here we're seeing the contouring of bending moment in MXX, which is essentially the bending in the XX direction. Remembering with 2D elements, the bending is in the direction of the axis and not about it. So we can see the kind of image that we expect. We've got sort of sagging in the midspan, we've got hogging over the columns. Again, we're looking at bending in the XX direction. But we can go a lot further than this. We can use contouring, as I said in the lectures, to really help us understand. So maybe to start with, what I want to look at is the region in sagging. So I'm going to come back to the contouring options. If I change the maximum to 0, Robot's telling me that the largest sagging value is -159, so let's just change that to 160. If I wanted to, I could change the number of contours, but now that I've changed these two values, the important thing to remember is to now come to the drop-down above, change that to user-defined. That will now apply that to the diagram. So if I hit apply, we can now see that the contouring's changed. It's going from 0, which is what we defined, to -160. So now what we're seeing, again, is bending in the XX direction, in the direction of the x-axis, but we're only seeing sagging. So again, it can really help us now to kind of focus on one specific aspect of the structural behaviour. If I maybe didn't want to see the contour map, or maybe found it a bit too much, I can come down to the options here. I can turn on isolines. If I hit apply, so this essentially shows you the contouring of moments. If I wanted to, I can come back and turn on the description. If I hit apply, you can see now that's now applied the contour value. If you zoom in a lot, you can hit the button up here, the green redraw arrow, and that should redraw the diagram to the view that you're looking at. So that might give you more information in terms of the contouring annotations. But let's take that off. Let's go back to the maps view. So that's good, but we can again go just a bit further. So maybe I know that I've got a background mat of reinforcement. So that might be, for example, 12mm bars at 150 centres. And I know I can do a simple calculation that would tell me that perhaps I might have a moment of resistance of 40 kilonewton-meters per metre. So what I can then do is I can come back to the contouring, because here on this diagram I'm showing everywhere where the slab is sagging. But what I really want to do is to identify areas where the sagging moment is higher than the resistance of my basic mat of reinforcement. So I can come back to the options here, change it back to linear scale, which opens up the dialog here. I can change that to -40, so I'm saying that's my base resistance. The thing to remember is to come back to the dialog here and change this back to user-defined. That then locks these values in place. If I hit apply, you can now see it's essentially sort of changed the contouring. So the lowest value is -40, and again, the highest is -160. I'm assuming that that's a numerical peak. But what this is telling me is that if I've got a base mat of reinforcement, and again, just as an aside, in terms of a way of approaching design, it's often, I think, a good way to approach the design of reinforced concrete slabs, to think of the buildability, to think of what a standard mat of reinforcement might be for your particular case, what the spacing of the bars might be. You can work out the resistance, and then when you're looking at design, really what you're looking at is how to enhance the reinforcement, maybe by placing additional bars, or maybe by locally increasing the bar size to give you the resistance that you require. So it's telling me here that in the zones that are highlighted by the colour map, that's where I need to enhance the amount of reinforcement. So I think contouring is a really powerful tool, as I said in the lectures. So now, if I go back to a linear scale to essentially reset it. So before moving on, I think it's important to remember that this isn't actually correct in terms of the design of the reinforcement, because I'm looking here at MXX, the bending in the XX direction. I can change that to look at the bending in the YY direction. But because I haven't taken out the torsional stiffness of the 2D elements, there will be, to some degree, torsion in the slab as well. And as you'll know from your lectures, to get the design moments for the concrete slab, you need to include both the bending in a given direction plus the component of torsion. So there are various ways of doing that. You will probably have covered the wood armour rules as one of the standard methods of taking a moment field and converting that into a design moment. So, if I get rid of my results. So some software, and it's true of Robot, will actually give you that derived output. So in this case, it's in the Complex tab, and you can see here we've got an option to choose how we're going to calculate the moments associated with the reinforcement. So there's the option for the wood armour rules and also the NEN rules. So these are, I think, are the Dutch rules, which are a more streamlined or simplified version of the wood armour rules. But I'll switch back to wood armour. And what this allows us to do is look at the moments in the slab at the top and the bottom faces. And that is then further subdivided into the top in the X direction and the top in the Y direction, the bottom in X and bottom in Y. So I'll look at the bottom reinforcement in the X direction. And again, I'm just choosing these options to illustrate how Robot works. Again, I think it's quite intuitive, but there's always the help menu here, which will take you to some quite detailed help to give you an explanation or a more detailed explanation. So if I hit apply, so essentially here, this is now the moments that you get if you go through the wood armour approach. And again, I'd recommend you test this out. You should maybe do a hand calculation to confirm to yourself that the software is actually doing the calculation correctly. So again, these are the wood armour moments. These are what you would design the reinforcement for. But again, it would be exactly the same principle as I've just discussed. We've got these bending moments. We might know that our resistance is the 40 kilonewton meters per meter. So again, I can come to here, change that to minus 40. That's my base resistance. I'll choose a smaller value because I don't really think the high value is representative. I think it's just a numerical peak. If I change this back to user defined, if I hit apply. So again, here I'm using the wood armour rules. I've got my wood armour moments, and I'm essentially showing where I need additional reinforcement beyond the resistance of the base mat of reinforcement. So again, I think it's a really useful way of thinking about concrete design. And of course, we can do this in the other direction and also on the other face. The other thing I just want to mention here is that if you've gone to the trouble of setting up your resistances or some other sort of contouring here, you really don't want to have to do that every time that you start the software. So what you can do is once you set your contouring up, if you come to the Save option, you can then choose to save that. So then the next time you open up the model, you can choose Open, you can choose your contouring file. Actually, I'll do that. And again, give it a name for the direction. And perhaps the face, depending on what you're doing. If I now open, I can see here, I can sort of open up the contouring. So just finally on contouring, here I've gone to linear, I've changed the actual limits. But what you can also do, and I'll maybe change back to isolines with a description to show this. So here we've got our contouring. But the thing I can do is that I can come directly into the contouring color bar. I can choose to switch some of these contours on and off, again, depending on what I'm actually going to do with the actual data. But I can click on the actual contouring value and maybe say if I change minus 53 to minus 50. And when I hit apply, you should see the minus 53 contour here change position slightly and be relabeled. Yeah. So there we go. So there's a lot of things we can do with the contouring to help us with our reinforcement design, or just interrogating and understanding our models. I'm doing this with moments. We can obviously do it with stress and also with displacement as well. So if we've got displacement limits, we can use that. But again, obviously with reinforced concrete, we can't look at displacements or elastic displacements. We need to maybe think of a cracked analysis, which is a much more complex type of analysis. So the last thing that I'll do, and I'll again reset the contouring. So the last thing I'll do is just maybe do the same thing, but for shear. So remembering that when we're looking at maybe the shear strength of the concrete, that's effectively a principal resistance. So we then need to look at the principal through thickness shear stress or through thickness shear force. So in Robot, we've got the principal values here. And if we come down, we can look at the principal shear force or the principal through thickness shear force. And again, if you go to the help menu, you can get a detailed description of the sign convention and what all of these options will actually display. So if I choose apply, so it's showing me the isolines. I think that's because I haven't switched it off from before. Just for convenience, I'll start with the map. So as you would expect, we've got the peaks of through thickness shear stress, essentially punching shear around the columns. Interestingly, if I look at the blade walls, we can see, as we expect, we've got high shear stresses around the ends of the walls, but not much in the centre. Again, conforming to expectations that it's the ends of the walls, it's the ends of blade columns that attract the high shear stresses. But personally, I don't think it's that easy to work with colour maps, so I'll go back to the isolines. So why might I want to look at this? So I think looking at through thickness shear stress is a really good way of understanding punching shear and also informing the punching shear design process. So we can use these contours to help us understand where we've exceeded the shear resistance of the concrete and hence where we might need sort of shear links. It also tells us, as I said, where the peaks are, perhaps at the end of columns, at the end of blade columns, at the ends of walls, at the corners of walls. So it again informs us, it helps us to maybe focus in on areas that might be important in terms of the design. So in terms of the contouring here, again, I imagine that the upper values are picking up on the very high point through thickness shears. So I'm going to refine that a bit. So let's look at the column here. So you remember perhaps from the earlier on, what I've done is draw the shear perimeter. So just to remind us of that, that's the bigger square on the outside. The smaller inner square is purely just the shape or the size of the column itself, so I can switch that on. So if I go back to the top view, so that bigger square is essentially what I'm saying is the shear perimeter. Again, just for convenience, it's square, it's the old BS 8110 shear perimeter. Obviously, if you were using EC2 or some other code, you might have perhaps curved corners to this. But again, it's really the principle I'm discussing here. So just to have a look at what these values are, I'll switch on the description for the isolines, and you can see there. So I've done the calculation ahead of time, and I know that my shear resistance of the concrete section alone is in the order of 300 kilonewtons per metre. So I'm not going to change the extents, but what I'm going to do is maybe to create a contour here, change that to 300. So again, that's my resistance. If I choose apply. So we can see this contour of 300 kilonewtons per metre is what my resistance of the concrete alone is before we have shear reinforcement. And we're testing it against the control perimeter. So again, using this type of method is very much also a matter of a judgment. Are we concerned with this small area outside? I mean, the bulk of this contour is within the control perimeter, suggesting that we've got adequate resistance. We've got this bit outside of the perimeter as well. So that would indicate this area here and this area here might be overstressed. But again, this is an elastic analysis, whereas we know that punching is a more plastic effect. But again, these are the things you need to maybe think about and consider in doing design, certainly in terms of shear design. The other point here, and I'll turn off the descriptions of the ice lines just to make it clearer. The other thing to think about is that I'm using this perimeter and the contour to help me decide whether I have an issue with punching shear. And I would do the same around the blade wall as well. But it's then important to think of, well, we know that at these points, at these support points, the rate of stress is going to be changing quite rapidly. So we need to maybe think, do we have enough mesh? Do we have enough finite elements as we come into these support points? So I can turn on the finite element mesh. And again, zooming back into to the area there, I can see I've got my support there. I've got a few elements before we actually come to the perimeter. So again, in this instance, for this size of column, I think I'd be happy to accept this. But again, it's something you should think about and really make a judgment on a case-by-case basis. And as I said in the lectures, I really would encourage you to build maybe small test models to examine these types of things, to examine the behavior, to look at how much mesh, what mesh density you really require to get a robust model. So I'll turn that off. So hopefully that's been of help. Again, contouring can be really helpful both for us as designers, but also if you're going to explain your work to other people, using contouring can be a really visual way of explaining the design that you've carried out. So in the last part of this video, I'm going to talk about panel cuts. So in Robot, that's essentially a way of defining a cut line on our structure, and then we can look at the results, whether that's moments, shears, stresses, deflections, etc., along that particular cut. So it's a really powerful way of helping us to interrogate the results of our analysis. So I'll go to a top-down view. And if you look in the Results tab, you can see panel cuts. If I click on that, the panel cuts dialog appears. And I want to define a cut line between 2 points, say. There's various options here. Again, if you look in Help, you can get more of a description. And what I want to maybe do is define my cut line between this column and the column there. So I've got my cut line between 2 points selected. If I click on the first box, it's then expecting the input for that. And you can see it's snapping to the background. So again, if you wanted a panel cut between 2 points that aren't already defined, you could maybe put that onto the CAD background. So again, thinking back to the earlier part of the talk about the benefit of having a CAD background that's linked that you can update. But we want the cut line to go between 2 columns, so the points are already there. So you see it's snapped to the next input box. If I click that, that's my 2 points of the cut line defined. It's automatically given it a name and a color. Again, I can change these if I wanted to. If I click Apply now, we see a number here, which I'll come to in a bit, but that's the cut line, but it's not especially clear. And that's because it's drawn out of the plane of the slab. If we rotate the view slightly, again, you can see that. So you've got the name of the cut line there, you've got a value there. It's looking at in this case, the shear force, just because that's what I had it on before I started the model. Just before going to that though, if we look at the Cuts tab, you can see the cut that you've defined, so you can have a whole series of panel cuts that you can turn on and off for ease of viewing. But if I come to the Principal Stresses tab, turn that off, and maybe I want to look at the bending along the direction there. So remembering again, because we're looking at 2D elements, that bending, that XX bending is essentially bending in the direction of the x-axis. So I go to Moments, XX, choose apply, and there you can see the results. And again, thinking back to the lectures, it's as we'd expect. We've got hogging at the supports, sagging at midspan, and hogging at the other column as well. And I can just change the actual view if I want to maybe see that a bit clearer. But maybe you don't want to keep turning your view from the plan view to the side. So what we can do, if we scroll along the top of the panel cats dialog, we can go to diagrams. And there's a range of options here for both the labeling of the diagram itself and whether you actually want the diagram name. But we can also choose how the diagram for the cat line is displayed. So it can either be normal to the plane that we're considering, which is what we're showing now, or if we maybe want to always look at the view from the top, we can change it to be in the plane of the slab. So I could choose that, hit apply. So now we don't need to turn back and forth. We've got the bending moment in MXX, but it's just been shown in the plane of the slab. So it's a much easier view to work with, I think. So again, you can maybe start to see the power of this. You can define areas of your slab. You can look at cat lines, perhaps as a way to check what the moments and forces are, or perhaps for design itself. So that's looking at moments. But let's perhaps just look at the shear force, because I think we can do a lot more with the panel cat feature. So I want to maybe look at perhaps the shear here. So we've got my fin columns. I want to maybe look at the shear stress or the shear force in the slab on a cat section here. So again, it's the same thing. I come back to my panel cats dialog. I choose new because I want to create a new cat. That's just given me another color and updated the name again. As I said, I can change that. Just for convenience, I'm going to get rid of those coordinates from the old cat. So I now want to define my cat here. But you see nothing's happening because there's no background, there's no structure defined for the cursor to snap to. Now we could obviously sort of put in something here maybe in the background or create a dummy piece of structure. But if we don't want to do that, we can come down to the bottom left to these small toggle buttons I mentioned right at the start. And the one on the leftmost side is the snap settings. I'm sure there's a way to get it from the menus or to create a bespoke icon. Again, I can't quite remember. But once we've got the snap settings, if we just turn them all off, and now you can see the crosshair has appeared on the screen, so it's not being confined by defined points. Essentially now there's no snapping. So if I move my snap settings to there, I want to now come back to here. I've selected the first input box for the coordinates. Maybe I want my cat line to start there. Maybe I want the next cat line point to be there. If I hit apply, you can see it's appeared. Again, because we've chosen to show diagrams in the plane of the slab, and that's why we're seeing it, as you can see there. If we go to cats, you see it's been defined. If I just maybe turn off the other cat and choose apply, you can see now that's been removed. This diagram's been rescaled. So again, that's something else to think about when displaying things, whether it's cat lines, whether it's contouring. By changing the parameters of the contouring of the value range, again, that will change how things are actually displayed. So I want to look, in this case, at the through thickness shear force on this particular line. So I'll turn off the XX, which has been displayed, so there's nothing now shown. If I go to the tab for the principal forces, I've got the option here for the shear force, the through thickness shear force, and I can choose apply. So that's what we can see there. But the interesting thing, and I think the useful thing, is what we're also seeing in the bottom right-hand corner. So yes, we've got the through thickness shear force being shown there on that cat line. But what this is telling us here is the integrated value of shear force is 298 kilonewtons. So essentially it's integrated along this for us. So that can be really helpful if we want to define perhaps shear perimeters to get the total shear force on a given perimeter. So it can be really helpful, a really powerful tool in helping us with our analysis and interpreting the actual analysis itself. I hope you have found the short Getting Started video for Autodesk Robot useful, and that it will allow you to quickly get to grips with the software if you're picking it up for the first time.